Assalamu alaikum and hello again. In this video, I will be doing the third homework for the control systems one. Here in the homework, I have 4 questions which I have to solve them all. Starting with the first one, here I have this block diagram. Actually, this is the same one from the second homework, so I will do it very fast. Here for this section, I can add these two together, so it will be 1 plus G2, and I will move this to the right, so it will be G3 divided by 1 plus G2. So it will be like this. Here I have the input, and here I have G1 multiplied by 1 plus G2. And for the feedback, it will be G3 minus 1 minus G2 divided by 1 plus G2. Now here I have to eliminate the feedback to obtain the final transfer function. So it will be like this. In the top I have G1 multiplied by 1 plus G2. And here in the bottom I have 1 plus. Here I'm adding because the feedback here is negative. So it will be adding here. It will be 1 plus G1 multiplied by 1 plus G2 multiplied by the feedback transfer function, which is G3 minus 1 minus G2 divided by 1 plus 2. Now for this 2 here, they will cancel each other, and the final transfer function will be like this. G1 multiplied by 1 plus G2 divided by 1 plus G1 multiplied by G3 minus 1 minus G2. And this is the final solution for the first question. Now moving to the second question, I have this function in which I have firstly to linearize it. To do so, I have the linearized formula will be like this. Will be here I have v of h naught plus the differentiation of the function in respect to time, then multiplied by h minus h naught. Here h naught is 3, it's given in the question. Now for this part here, it will be 5 multiplied by 1 minus e to the power negative 0.2 multiplied by 5. And here plus, if I differentiate it here, this part here is constant, so it will be 0, and I will have minus 5 multiplied by the differentiation of the exponential, so it will be e to the power negative 0.2 multiplied by h naught, and here I have to multiply it by the differentiation of this part here, so it will be multiplied by minus 0.2, then multiplied by h minus 5 h naught. Now for these two here, they will cancel each other, and the final form for the linearized equation will be h of v will be equal, this part here will be evaluated to be 3.16 plus, and this exponential here, it will be 0.368 multiplied by h minus 5. So this is the solution for the A section. Now if we move to the B section, here it says I need to compare it to the actual model for h equal 5 meters. So for the actual model, it will be equal to 5 multiplied by 1 minus e to the power negative 0.2 multiplied by 5, and, and it will be equal to 3.16. For the linearized version, it will be 3.16 plus 0.368 sorry, multiplied by 5 minus 5. This part here will be 0 because 5 minus 5 is 0, and the final value is 3.16. So as we see here, they both equal, and the relative error is approximately 0%. For the C section, it's same to the B section, but here H is 5.5. So for the actual model, it will be 5, 1 minus e to the power negative 0.2 multiplied by 5.5, and it will be equal to 3.4. 1 minute. It will be equal to 3.336. For the linearized version, for 0.5.5, it will be equal to 3.16 plus 0.368 multiplied by 5 minus 5, 5.5 minus 5, and it will be equal to 3.344. So here the relative error is approximately 0.3%. Here it's 3.336 minus 3.344 divided by 3.344, 100%, and it will be equal to 0.2 for 100%. So this is not. Moving to the third question. Here I have this circuit, and for A section I have to derive the dynamic equation for it. So here it is. Here the total voltage drop across these three elements should be equal to the V input. So I can write Vn يساوي Vn equal to the voltage drop across resistor, which is I times R plus L di over dt plus Vc. Now for the current here in this equation, we know that the current across the resistor and inductor is similar to the one across the capacitor, and for the current across the capacitor, it can be written as C multiplied by the differentiation of the uh, voltage across the capacitor in respect to time. So here I can rewrite it rewrite it as Vn equal to Rc dVc divided by dt plus Lc second order differentiation for the inductor, which is in respect to time, plus Vc. And this is the dynamic equation for the given circuit. Now moving to the B question here, it requires me to obtain the state space representation. So first since I have second order differential equation, I have two state variables. These are x1 and x2, and I will set x2 to equal to the differentiation of x1, and for x1 it will be equal to bc. So x2 will be equal to dvc divided by dt, so that the differentiation of the second variable will be equal to second order differentiation of uh, bc in respect to time. Now I will write the skeleton for the state space. Here I have x1 and x2. Here is the state matrix, and this is the state vector x1 and here x2, and I will add to them the input matrix. Now for the first value, it's equal to x2, so here it will be 0 and here it will be 1. For x2 differentiated, if I bring back the differential equation, which is Vn equal to Lc second order differentiation of Vc in respect to time plus Rc, and here it's Rc dVc over dt plus Vc. I can take these two to the left and then divide them by Lc, so I can obtain this uh, I can obtain the second order differentiation alone in one side. So here it will be Vn divided by Lc minus Rc divided by Lc times, and this one here is actually x1 differentiated, and here plus Vc, sorry, minus Vc, which is x1, and divided by Lc. So for x2 differentiated, it, it will have one input that is divided by 1 by Lc. So here it will be 0 and here 1 over Lc. And for the state matrix, here I have x1 differentiated, which is x2. So and it will be equal to r minus r over L. So here it's minus r over L. Actually, no, it will be here minus r over L. And this one here, it will be minus 1 over LC, minus 1 over LC. Now for the output matrix, Here in the question it's given the output is VC, and since x1 is VC, the output matrix will be 1, 0 multiplied by x1, x2 plus, and the feed through matrix is 0. And this is the solution for the second part of that question. Now for the third part, here it requires me to obtain the transfer function. So if I bring back the differential equation, here if I take the Laplace transform for this part here, it will be Vn s will be equal to, here the differentiation equals to multiplying by s in the Laplace domain, so it will be s rc multiplied by vcs. And for this part here, since it's second order differentiation, it will be multiplied by s two times, so it will be s squared lc vc of s. And for the third term, it will be vc only. Now here I can take vc as common factor and divide it by vn, so it will be vn over vc will be equal to src, so s squared lc plus rc s plus 1. And since the transfer function is actually v out over vc, I will flip this equation, so it will be vc over vn will be equal to 1 divided by s squared lc plus rcs plus 1. And this is the solution for the third section, for the third question. Now for the final question, I have this transfer function in which I have to obtain its response in the time domain for a unit step input and the unit ramp input. So to obtain the time response y over y of t, it will be equal, sorry for that. Now to obtain the response in time domain, first I have to obtain the output in the s domain. It will be equal to gs multiplied by the input, which is 1 over s for the unit step function. So it will be 1 over s multiplied by, here I have s multiplied by s squared plus 3s plus 7. And here for the denominator, I can decompose this part here to be equal to, I can decompose it to s plus 7 multiplied by s plus 3 and then multiplied by s plus 1. So these two will cancel each other, and for this part here I will add 5s and subtract 5s. Now if I add this to this part here, it will be s squared plus 8 squared plus 8s plus 7, which I can decompose into s plus 7 multiplied by s plus 1, and here I have s plus 7, s plus 3 multiplied by s plus 1, and then I have s minus 5s over the same denominator. So here these two will cancel each other, and this one also will be cancelled with this one, and I will be left with 1 divided by s plus 1 plus 3. Sorry, not this one, with this one. So I will have 1 over s plus 3. Now for the second one here, I can perform partial fraction decomposition. So here I will have a over s plus 7 plus b s plus 3 over s plus 3 plus c over s plus 1. Now if I solve for a and b and c, they will be equal to, just 1 minute. Now for a it will be 35 divided by 24, and for b it will be equal to minus 45 divided by 24, and for c it will be equal to 10 divided by 24. So if I evaluate it now, if I evaluate this one here for any 1 over s plus a, in the time domain it will be e to the power minus 80. So the final output in the time domain, it will be equal to this one here, it will be equal to e to the power minus 3t plus a, which is 35 divided by 24 multiplied by e to the power minus 70, and for b it will be 1 minute, and for e it will be minus 45 divided by 24 multiplied by e to the power minus 3t plus, for the last one, the c1, it will be 10 divided by 24 multiplied by e to the power minus 1t, and this is the solution for the A part from the last question for the unit step input. Now for the B part, it's asking for the unit ramp input, and so it will be equal to, in the S domain, it will be equal to GS multiplied by 1 over S squared, because ramp function has 1 over S2 in the Laplace domain. So it will be equal to 1 divided by S squared multiplied by S multiplied by S plus 8S plus 7 and then minus 5S. And here it's divided by S plus 7 multiplied by S plus 3 multiplied by S plus 1. Now here this 1S from here will be cancelled with this one here, and if I take this out into another fraction, I can decompose this into S plus 7 multiplied by S plus 1. So in the end it will be 1 divided by S multiplied by 1 S multiplied by 1 over S plus 3. And for this one here, I can again do partial fraction decomposition, and it will be equal to, actually for this S here it will be cancelled again with this one. So at the top I will have only minus 5. And if I do partial fraction decomposition, it will be A divided by S plus 7 plus B multiplied by S plus 3 and then plus C divided by S plus 1. And for this one here, I can again do partial fraction decomposition. Here I will do it very fast. For the first section, for 1 over S, it will be 1 over 3 multiplied by 1 over S plus, and for this one here, it will be negative of this value here. So it will be minus 1 over 3 multiplied by 1 divided by S plus 3. And for the values of A, B, C, 1 minute. So for A it will be minus 245 divided by 24, then multiplied by 1 over S plus 7. And for B it will be 45 divided by 8 multiplied by 1 over S plus 3. And for C value it will be minus 10 divided by 24, then multiplied by 1 over S plus 1. So if I transform this back to the time domain, for this part here, it will be unit step function. So I will have 1 over 3 multiplied by u of t, and here minus 245 divided by 24 multiplied by e to the power minus 70 plus, and here it will be 45 divided by 8 multiplied by e to the power minus 3t, and here it will be minus 10 over 24 multiplied by e to the power minus t. And this is the solution for the unit ramp function in the time domain. And that's all for this video.